actually scouting for some data science program, and then I got to know there was very few players who were actually giving this PGP full-time program, and Aegis was one of those. I was actually scouting for some data science program, and then I got to know there was very few players who were actually giving this PGP full-time program, and Aegis was one of those. I was actually scouting for some data science program, and then I got to know there was very few players who were actually giving this PGP full-time program, and Aegis was one of those. I was actually scouting for some data science program, and then I got to know there was very few players who were actually giving this PGP full-time program, and Aegis was one of those. I was actually scouting for some data science program, and then I got to know there was very few players who were actually giving this PGP full-time program, and Aegis was one of those. I was actually scouting for some data science program, and then I got to know there was very few players who were actually giving this PGP full-time program, and Aegis was one of those. I was actually scouting for some data science program, and then I got to know there was very few players who were actually giving this PGP full-time program, and Aegis was one of I was actually scouting for some data science program, and then I got to know there was very few
end-to-end, highly scalable, cloud-based digital infrastructure and modular solutions powered by Amazon Web Services. No need to deal with several vendors and deploy their silo systems, resulting in higher cost, inefficiency, and security risk. Crowdsourced best practices for running a higher education institution. Design perfect courses with the help of AI tool and big data analysis suiting to industry demand. Get insight about skill and job
Tushar, can we start? Priyan? Rajat, good morning to you. Can you kindly unmute yourself, please, Rajat? This
Yes.
is Vinay Kulkarni here. I think
Yeah. No. Can you hear me?
Start without any further delay. Let me start with apologies for the slightly late start to this particular session. Obviously, it was because the opening plenary session took some time. So welcome everyone and good morning to you. After the tone set by the speakers in the plenary session, we are now entering into very specific talks, which I think are going to be extremely interesting. So without any further ado, let me introduce to you the first speaker for the first session today, that is Rajat Monga. He's going to talk on AI is changing the world. Why is it taking so long? Rajat is the co-founder and former lead of TensorFlow, and he was part of the Google Brain team that powers machine learning research and products worldwide. As a founding member of the team, he was involved in co-designing and co-implementing Disbelief and many more, and more recently TensorFlow. Prior to this role, he led teams in Aegis, built out the engineering teams and co-designed web scale crawling and content matching infrastructure at Attributor, and co-implemented and scaled eBay's search engine. Rajat has a BTech degree in electrical engineering from the Indian Institute of Technology, Delhi. And he has recently left Google to bring machine learning into some key aspects of the business world. It would be very interesting to listen to you, Rajat. It's all yours. The stage is yours. Please go ahead. You have about 40 minutes to talk on. Don't mind if I ring a bell or two just to remind you about the time, and then we'll get into the question answers. This is Vinay Kulkarni here from Aegis.
Yeah, thanks, Dr. Vinay Kulkarni. Thank you for that introduction, and pleasure to be here today. So, we hear a lot about AI, and of course, this whole session is really about AI. There's so many different things that we look at. So, we've heard of so many amazing things that AI has been doing over the last few years. So first, I'll go a little bit into that, and then beyond that, wanted to see what are some of the things slowing us down, or why aren't we really getting to where we want to be in every place across the board, right? And how can we help? And so let's take a look first on, where are we with machine learning so far, which is sort of the biggest piece of AI that's really made things move forward currently. And the first piece here, one of the early pieces is vision. And if you think about where deep learning came from, that field itself is very old, and it's been, neural networks have been around for 30, 40 years now, maybe longer. But it's over the last 10 years that we've seen this huge resurgence. And one of the earliest things that we saw that come with was vision, for a number of good reasons. So, one of the data sets that everybody talks about, and some of the numbers that I'll talk about, is based on this thing called ImageNet, which is basically the core data set is about 1 million images across 1,000 different categories. And these are categories like not just, cat and dog, but very specialized kinds of cats and very specialized kinds of dogs, something that even humans are not amazing at. They don't get it right every time either. So let's take a look at where we were back in 2011 when some of this resurgence started, this sort of second innings in some sense. And back in 2011, humans for this particular data set were at 5% errors. So, we didn't get everything right. Out of 100, we would get about 5 wrong. Whereas computers at that point were in 26% errors. And this is, after making a lot of improvements and stuff. And so we're still far behind where computers were back then. Now move forward. This is sort of like looking at this, some image of an animal that you can kind of make out. As a human, you can probably guess it's like a cheetah, but it's hard for a computer to guess that. Move forward a little bit. And we can see, it goes from there to basically 3% errors in just a few years. And what this led to was really kind of like back in the old days when, millions of years ago, really, in the progression of Earth and human or animals on Earth, where you suddenly had vision and you saw like this plethora of different kinds of creatures come up. And so this was a great, move forward. And let's see, what this led to in a couple of areas. So one, Google Photos, which now is pretty much, this kind of technology is really in every place, every application, and you expect it to be there. You don't really want to organize photos and think about labeling them in every way. That's just done for you. In this case, you can just search for dogs or pictures of, here's an amazing picture of a glacier back there. The other, side of things is, of course, vision is one. The other piece that works really well for us is hearing. And once again, this is something that computers were really bad at back then. And so, in terms of the improvements that happened over time, we can actually, not just can we type in those things, but we can just ask our phone, okay, show me pictures of cats, and it will show you a whole bunch of pictures because it gets that speech. Now, just to give you a perspective on how much deep learning changed things here back in 2012, the launch of change from the existing model to this new model with deep learning, the gain that we got there was equivalent to something like 20 years of research by all of the speech community combined. So all of that by this one change, and that's really what sped up the improvements in this area among others as well. What this led to is this is a product that's launched I believe earlier this year, where you can actually live caption any video right on your phone. And in this case, this person's has a cooking video. Maybe you can't really hear there, and what this does is it basically just turns on the live captioning. You can see everything written down right there live. Of course, these are probably two speakers that you're familiar with, whether it's Alexa or Google Home. And these speakers really came about primarily because of this huge change, where we are changing from this mode of typing and everything to really asking for things that we care about, and we are starting to get really good answers for those. Now, number 3 there is, of course, the vision and speech are great, but really understanding language. So even when we talk to a computer, one of the key pieces is, does it really understand that language, and what can we do with it? And it's not just for speech, of course, it's also for something as basic as search that you do, or do some, anywhere across your chats, etc., etc. So in this case, one similar data set that has been used, sort of a computation that's been used to track progress for humans or these models versus humans, is this reading comprehension test. And this was created a few years ago, 2018, not that far ago, right? And where humans had a score of 86 in this, or an F1 score of 89, it took us a couple of years, not very long, where we now have models that do better on reading comprehension on the specific test than humans itself. So think about it this way: if you had an exam and you could have this model actually go through all the stuff that you were supposed to read, it would probably do better than the average human there. Of course, I don't think it's going to be available for most of you, especially if you're students. I think you'd still have to do the learning for now. So now, looking at what impact that's had in this short span, really, this is an example of what was happening in Google search before and after for a more complex query where you're asking for a specific thing. The first one was really just taking those keywords and trying to put those together and match documents that have all those keywords. Whereas now it actually understands the specific intent here in terms of traveler from Brazil to the US, visa needed for them, the right kind of tourists, and putting all of that together really makes a big difference. And we've made a huge leap in how we understand language now. So, we've talked about these 3 different domains, and let's take a look at how it's been impacting different kinds of products. One, again, going back to translation, here you have right on your phone, Google Translate can actually detect the language, convert it to your language from a picture. So it's basically recognizing that there's text, doing optical character recognition to recognize what text it is, what language it is, and then translating it to your language and then displaying it with AR. And not only is it in that application, it's also integrated into a bunch of other, you can access it on most Android phones today. Here's an example with WhatsApp where you can translate from one language, translate or understand different languages as well. Really allowing us to communicate across boundaries, across different kinds of places as well. Here's an example of combining a number of technologies around vision, where it's always hard when you're trying to take a group picture to get everybody aligned and stuff. And in this case, with the photo booth, it's just figuring out, you turn it on, it's going to figure out when everybody is aligned, when's the right time to take that picture and take it for you right there. And finally, here are a bunch of hardware products that Google launched last year. And pretty much every single one of them has machine learning being used in different kinds of ways. On the phone, of course, for the camera itself, for lots of other things, for the hearing part, using OK Google and a number of other things, and so on, really across the board for every single piece. We talked about a number of applications. One that's really close to us that really impacts our lives is healthcare, which really changes how we do things. And there are a couple of areas that we've made a lot of progress there as well. This one is in terms of just really understanding how things are in eyes. And these are pictures of the back of our eyes called fundus images or fundal images. And here it's trying to detect diabetic retinopathy in patients. Turns out it's a very common disease, especially in places like India. And often folks across the board don't have access to the doctors. And so being able to detect this, and in this case, turns out this model can do actually much better than most doctors can. So you can ship this to all kinds of places and really scale the access to doctors to lots more people. And of course, something that's much closer to us today, with COVID-19, there have been lots of things that are happening, and AI has been really at the forefront of helping scale up things and really make progress in what we can do. In this case, a company in India called Cure.ai has basically been able to look at chest images and really help you diagnose if the patient has COVID-19, what's the risk for them, et cetera, independent of some of the other tests as well. And so something that we're seeing right in use right today and really makes a big difference for us. So, we talked about a lot of things that AI has enabled. Now, to think about what kind of things are we, what's really happened over these past years that's really allowed us to grow this? Of course, there have been improvements in the hardware itself, improvements in algorithms as well. But beyond that, there are a number of other things that are needed as well. And one of them, I believe, is tools. In this case, here's a hammer. If you want to do something, if you have a hammer, you basically think of everything as a nail. And so you are basically going to be hammering every single thing. And you're often limited by what you can do by the tools that you have. So let's go back a little bit and see how things were a few years ago. Back when we started 2011 timeframe, NumPy was still very common from a Python perspective. And if you wanted to do MNIST, which is sort of this really small machine learning for vision example that researchers did for lots and lots of years, which basically has 60,000 images of just characters 0 to 9, and it's trying to classify them. Now, just to do these images, basically, it needed to, here's how you set up it. So this is page 1 of the code that you have. Keep going, you really define not just the basics, define your parameters, define the functions, define your actual function for the, defining the layers and so on, what it does. And you don't stop there, right? You have to, because there's no automatic back propagation or whatever, you actually have to specify the gradients that are there. And in fact, when I started in this field, this is sort of where we were. And now this is the training itself. You're going through all of this, this ends up being something like 6 pages of code that you have to write just to get that MNIST example going. And think about all the errors that you have, all the time that you spend in just fixing that code. This is really the state was just 10 years ago, not that long ago. And in fact, here, if you're familiar with the person here, Geoffrey Hinton, who won the Turing Award about a year ago for deep learning, he's very well known as the father of deep learning. He along with Jan LeCun and Yoshua Bengio won the Turing Award. He's been responsible for a lot of research improvements in this area, and he's been at it for the last 20, 30 years. For him, the tool of choice was MATLAB. And most of the time he was playing with that one MNIST example in MATLAB, and that was his tool of choice. But he was able to make a lot of progress on that over the years because he really understood that well. And he was looking at a very small problem in some sense. Now, move forward a little bit. And, this is one of those networks that really changed the game for vision in leveraging deep learning. This was created back in 2012 by a person called Alex Kraszewski, working with Ilya Sutskever and Geoffrey Hinton himself. And this was fondly called AlexNet after him later. And this was, he designed it by hand using a very custom tool, handwritten tool, that took advantage of GPUs that were starting to be available. Now, GPUs initially were basically graphics processing units. They're in pretty much every computer that you see, mostly to drive your screen, and they were used in high-end graphic stations and so on. And what he was able to do was really program them to do all the computation that this was needed for this, really speed things up. And so all of that custom work really allowed him to make progress from where things were, improve things by something like 20% on that ImageNet example. This was the first time that instead of doing that handcrafted features in vision, we were starting to see deep learning make a huge difference. Now, move forward a couple of years, and this, if you think about the last one that had maybe 10, 20 layers, this one has, each box there is sort of a layer, and so something like 100 layers, and stacked like 20, 30 of them with all kinds of different things. This network is called Inception, and this was sort of the next generation in some sense after AlexNet, which gave another significant jump in improvements on that vision example. And this was built with a tool called Disbelief that we built back at Google back in 2011, 2012 timeframe. And having that tool really allowed this person, Christian Zagady, to really be able to build this and try this out, because he needed to run this across lots and lots of machines. He ran, I don't know, hundreds of experiments across each of them, across maybe tens to hundreds of machines. And this could only be done because there was a tool available for this person to do this. Moving forward again, this is for language models. And here we have, BERT versus OpenAI's GPT. And these were built, this huge improvement, BERT was one of the significant jumps in natural language itself that allowed us to really beat that squad benchmark that we were talking about. People have been building on top of that. That was enabled by having TensorFlow, which was in some sense the next generation platform after Disbelief that we built at Google, to allow, and in fact, natural language was one of the areas that really inspired us to push things and move things forward. Now, if you keep going, going back to that same MNIST example that we were talking about, that this is that same example doing the exact same thing, and you can now write it in just one page of code, just this little bit. So if you think about all the little things that you not have to worry about, think about what more can you do now that has been simplified. And this is possible because of TensorFlow 2.0 that came out last year. So going across just 10 years, we've seen this huge improvement from a tools perspective in terms of what you can do in terms of pushing the research forward in deep learning. Now that's great, but beyond the research, there's a lot more that you can do. If you want to build a house, just a hammer is not going to be enough. You maybe need a drill, maybe you need a bunch of other things as well. And so if you think about taking that analogy, going back to machine learning, we often think about the machine learning, the ML code, where we're building a model as sort of the key piece. But that's sort of just one part of the thing. In addition to that piece, that box that we were just talking about so far, we have all of these other boxes that you really have to worry about for making things work end to end. Because once you have the model, you still want to deploy to production. Before that, there are a whole bunch of things that you need to do. And to do this consistently across the businesses, across the world, in all the things that you want to do, having all these pieces is still a big deal. And so, for that, we have something called TensorFlow Extended. And here, the idea is to have all of these pieces that we were looking at in the last graph, really put all these pieces together and solve them for you. And a number of these pieces are now available in open source along with the core TensorFlow itself. And so I'll go through each of these pieces and just show you what they do. In the first piece is for data validation and something called TensorFlow data validation. And what that helps you with is really, all of these pieces that you're looking at, the first piece being, once you get data, you want to really understand what that looks like as you're building the model. So you decide what kind of model do you want to build, how many parameters you want, et cetera, et cetera. So the first piece there is to compute those statistics and just show them to you across those different fields. In this case, you can do that pretty easily from the data and whatever form it's coming. You can see this visualization as well. Now, once you have that visualization and you have gotten the basic idea, you want a schema that you're going to work off of to build your model. And this does that for you as well. It infers the basic schema that you can then work on. Like in this case, it looks at all of these fields, says this one's a floating point, this one's an int, this one's a string, and you probably want to treat it this way, and so on. And then once you've done all of those, now you have a schema. You want to make sure that all the data really follows that or matches that. And if not, maybe you want to iterate on that and so on. And so the next piece is, once you have those stats, you can take those stats in the schema and you can visualize the stats comparing two parts of your data to see how well they're looking. And here we are visualizing for 2 different days. This particular example is a Chicago taxi data set, which basically has a pricing and so on for different days in Chicago. And in this case, we talked about day 1 and day 2. In addition to just visualizing that, it also validates those by really comparing those along with the schema and surfacing any anomalies, anything that seems odd, anything that's changed over time, because you want to think about how you want to model that in a good way. Now, once you've done all of these, that's great. You're good to go in terms of training the model. Now, the other piece that often comes, how do you really know that the data that you're training on is the same that you're serving with? You typically assume that that's the case, but are you really sure? And so this is something that can help with in terms of when you're serving. It can also validate statistics while serving and doing it in a very efficient manner. So it makes sure that you are really serving and training on the same data set. And to give you an example, here's an area where here's a product, Google Play, that you probably have on your Android phone if you use Android, where we recommend applications that you should be looking at if you want to download the next thing when you go there. And for this recommender system, there are a lot of pieces that go in there, and we have personalized recommendations for you. Now, one of the things that happened is, we built a model and deployed it, that things were going great. But when we started to look and compare the data between the training, the serving, and the training, turned out that wasn't quite the same. And the tool that we built for this, in this case, data validation, showed us a huge difference. In fact, just by fixing that one thing, we got a 2% lift on that particular case. If you just spend the same kind of time in building the model or improving the model, we would have probably taken way longer. So, when you hear that looking at the data and understanding that and improving that makes a big difference, that is probably the number one thing. Once you have a basic model working, that's really the number one thing that you should make sure your data is in good shape. And that this really helps you with this. Now, the next piece, once you've validated the data and looked at that, is to transform it in the right form for your modeling to work. And here we have TensorFlow Transform, which really helps you there. And it serves a couple of purposes. So first, let's look at what it allows you to do. So you have these input features or input data elements that you want to transform to build the right kind of features for your model that you're trying to build here. And once you have that, that's basically that those functions are basically analyzed to create what we call a graph. TensorFlow internally uses graph. With TensorFlow 2.0, you don't think about graphs, but internally it still uses those. And the good thing about those graphs is it allows you to use those same graphs under the covers, both for training and serving, and you don't have to worry about it, right? And so when we're talking about the training serving skew, this is really helping you take care of that as well automatically under the covers. And so here's an example of some pre-processing function, what you might do in terms of creating those features. Here we are scaling one of the inputs, taking a string input and mapping it to an integer for a particular vocabulary, and in some cases bucketizing those. And here's some examples of the kind of transformations that you can do in terms of just scaling, doing a bag of words, or n-gram mapping, and so on. Basically taking a vocabulary in strings and mapping it to buckets in the right sizes, and so on. And finally, crossing different kinds of features, so combining two different kinds of features, and so on. And then you can also, in fact, sometimes what you want is the feature for one model might be the output of another model itself. And you can do that here as well. So we covered the input processing part, and then of course you come to the training itself. And I'm not going to spend too much time on this. This is a whole thing by itself. But here we basically support using the KRS model in an easy manner, which is well integrated with TensorFlow overall. And here's basically build a model. Once you save it. Now, once you've saved that model through Keras, you can really use it in the rest of the pieces as well. And now once you have that model that you've built and you've trained, which is often where you spend a lot of time in early on, but over time, the goal is to have that be just one part of it because you really want to solve all of these different pieces. And now you want to look at evaluating that model. Often while training, you look at the overall value. And so, where you'll see, is the model accurate enough overall, some top level number or some loss number, etc., that you're looking at. And once you have that, you typically think, okay, let's go on, let's deploy this and so on. Now, it turns out there's a lot more that you can do. So here, we just give that model to this model analysis tool and run that. And of course, the first thing it shows is, okay, what's that overall metric? It's showing the overall accuracy, overall AUC score, etc., the different kinds of things that you might take. And here's the baseline as well that it's comparing. Now, that's great, but how about different areas? Is the model really performing the same across all the slices? So let's take a look. In this case, we say, okay, let's slice those metrics by a specific spec. And in this case, we are looking by, this has different hours. So you can go all the way from like 12 a.m. or 1 a.m. to all the way to 23. And it's basically slicing by that and trying to see, is the model as good across the day, or is it doing differently across different things? As we look at it, we can see that it's very different. We can now sort and look at and try to really understand the model better. Maybe the data in some areas is not, it's much smaller. Maybe it's optimized for the hours that just have a lot more data, etc. Right? And so just going through this often surfaces some very interesting insights, especially when you go from one model to the next. You want to make sure that maybe you're making the overall model better on average, but you're not hurting a certain style of customer or a lot more than others. You really want to be very careful about that, both from a biasing perspective. You might not have really happy customers if you do that. And so covering the customers that matter the most for you, optimizing the right way, this kind of slicing really allows to dig into those. There are more things that you can look at as well. The distribution across that, the precision recall curve, and along those slices as well. And now you have a model, you validated that it's doing great. So what do you do with that? Now you probably want to serve it. You want to run it across the data, and you want to query it for lots of new instances or examples while you're serving. And to simplify that piece, that scaling it up can be hard. Sometimes there are a number of things that you want to think about. And to support you with that is something called TensorFlow Serving, where you can take that model and just run the server that's pre-built for you if you want, and just run that on a port, and you're up and running. You can make queries to this at this point. Here's a very simple Python example that basically creates a proto buffer, sends that as a query to this, and gets back results. And you can do that at a fairly high scale. You can scale it up many different ways and stuff. You can also have a timeout and other batching and so on that makes sense for your examples. Now, maybe in this case, we're using proto buffers, but maybe you're more used to the REST APIs, and that's what the rest of the systems use. And so you can do that as well. Here's a REST API that you could use. And to get that started, all you need to change is instead of the basic port, just say REST API port, and you can start serving this. Here's an example using curl that just runs that and gets back some JSON results for you. So really trying to simplify all the way from data to serving itself. And now to really put all the pieces that we talked about together, here's starting from the training data itself. We validate that data, look through generate the schema, validate, identify any kind of anomalies, etc. over time, make any kind of transformations on the data itself. Then once we have that transformed data and that graph, which can be used both for training and serving, we go to the modeling itself, leverage Keras model to build out and train these models. Save that model, make sure it's good before we deploy it, and then we deploy it. And so we support really that entire life cycle. And in fact, in this case, we talk about once you've served the model, you probably want to log those outputs, log both the inputs and the outputs. So those logs can go back in terms of data validation, making sure there are no skews, etc. Also making, going back to merging into the training data so you can continue improving your model itself. So we looked at all of these pieces, that are available. In fact, Those are available in open source today, so you can try them out. You can use them. There are a number of other pieces as well that are coming over time. And if you are a person who likes bowling, this is the kind of picture that you want to see while you're bowling. And this is really what experts can do with bowling, where they get a strike every time. Pretty amazing. But it turns out most people are not that good, and you might get strikes once in a while. If I go out there, I get a couple of strikes in a game, I'm happy. That's basically what I get. But a lot of people actually, what they get is this, a gutter ball. They're missing everything. And that's sort of the difference between what experts can do and what typical folks can do with machine learning today. Experts can really get things right today, but it's still really hard to get this, to make all of that work end to end. And this is where we often end up. So what TensorFlow Extended is really meant to be is really to provide what you see here, and even allow beginners to really get all of those things right, really be the guardrails for machine learning, where we can make things work right every single time. So that's one area that I think is valuable in terms of how we can make improvements, how we can really include and make AI accessible to a lot more people, and really see that change the world as we wanted it to be. Now, before I go, I did want to just look ahead a little bit and give you some examples of where we are heading in terms of newer things, etc. You probably heard of some of those, but some good and some interesting challenges that we also have to think about as we go ahead. And so here an example of what's an Amazon Go store. Now a number of other companies are building these as well. And the idea here is, you have a card, just go in, just walk into the store, just swipe the card and go in, pick up whatever you want, and there's no checkout. You just pick it up and go out, and you'll be charged for it. And the way they do it is they combine a whole bunch of technology, including vision to understand somebody's picked it up, to track who is picking what up, and so on. When you go out, really automatically figure out that you are the person who picked that up, and so charging you the right rate for that. And a whole bunch of these technologies are coming together to make this possible. You'll start to see more and more of these where you don't really need people to be around to check you out, etc. Especially in the kind of scenario we are in today with COVID-19, this really starts to make a lot of sense. Another example that we talk about all the time, of course, autonomous driving. We would love to see this today, or yesterday, in fact. But I mean, if we're not quite there, although we have lots of examples going around all over the place. Here's an example from Waymo, an Alphabet company, as you're probably familiar, that basically at the bottom you see these pictures of what it sees, and at the top its view combining all the 3D data, all the vision data to recognize what's going on, etc. We're making these very hard turns, in this case going left, where somebody's really coming in front and so on, and tracking, being able to do all of this. We're making huge progress in this area because of deep learning. So these are two examples where things are getting a lot, making so much improvements over the last few years. Now here's a different example.
At least not in a public address, but someone else would. Someone like Jordan Peele. This is a dangerous time. Moving forward, we need to be more vigilant with what we trust from the internet. It's a time when we need to rely on.
So, that looks like Barack Obama, sounds like Barack Obama, but as you saw in that video, it's some person impersonating as Barack Obama and really putting whatever words he wants in that mouth. This technology is available for lots of people today for using in all kinds of ways. And it's tricky because, in this case, of course, it's just an experiment to show that this is problematic, but people can use it for real things. Some good, some not so good, and some borderline, and depends on how you think about it. Here's an example from the Indian context. So this is the original video for this politician who many of you are probably familiar with. And during elections last year, what they did was take this video and really translate that into many different local languages, so it appears more personal. And this is actually a very, to me, it seems like it's a perfectly fine, legitimate thing to do. And it's not, it is with this person wanting to do this. It's not somebody else doing this. And so, it's a place, it's a way to amplify what you can do into many other ways. But there are lots of other negative ways that this can be used as well. So as we improve this technology, it's worthwhile to think about how this can be used and how do we use it in a good way. And so with that, I really, there's a lot of things that you can do. The technology has been improving really rapidly and continues to do so. The tools are making it easier for you to build things with this. And, in terms of what you can do, of course, the sky's the limit. It's really limited by what you are, what you think of, just as it says. And I would like to really leave you with what you want to do with this, and would also love to see all the kinds of amazing things that you build with this.
Thank you, Rajat. I think you have a few more minutes. You took much less time than you are allotted.
I have time. No worries.
Okay. So for the participants, if you have any questions, I think the best way out is to type them out in the chat window, and I will pick them up from there. But being the moderator, I think I have the privilege of starting off with the questions myself. So Rajat, here are some questions. I think, in your talk, you dwelt a lot on, validation of data as well as interpretation of results. Can we have AI or ML do that automatically? I mean, the other way of asking question is, how far away are we from not having to understand mathematics and statistics and the algorithms to really start using AI?
Yeah, so there's definitely a lot of progress happening in that area as well. What we call auto ML, where we are automating not just the training. Where it started was, okay, can we just automate all the tuning that you have to do in terms of building the model? What model do you want to build, etc. Starting there and slowly expanding in terms of, okay, can we really understand the data? Can we automatically clean up parts of it, or at least flag the right things so somebody else can look at it and stuff? And I think over time we've made a lot of progress. I definitely see us heading more in that direction. I think where things become, I would say, we would want to combine that with the right kind of developers as we are building the right applications on what do we want to do? How do we put together the right pieces for this to be automated, like the key piece, and really think about the business case for this. What is it, how does it really help what we are trying to solve for, rather than focusing on the nitty-gritties of the math. I think in some ways, tools like TensorFlow took away the math, took away thinking about the gradients or the algebra and so on, all of that. With this automation, we are taking away some more pieces where, the data cleaning or more of the understanding that you need to do. And which is useful because that makes it accessible not just to every researcher or say a data scientist, but to every developer out there, and maybe hopefully even beyond.
Well, thanks, Rajat. Another question, quick one from me itself is, we still talk about two kinds of people involved in developing solutions. The person who understands the domain and the person who understands ML and the math behind it. Again, the question here is, it's very difficult to combine these two skills, and it requires people to collaborate. And that perhaps was the reason why things like expert systems fell off long back. So again, what is your view on this? How far away from directly using the tools as a domain expert and not having to understand math again?
Yes. I mean, that is exactly the right direction to go. That's what I would love to see, and that's where that's what I work on as well. Over time, I think we're building the right set of steps. We are building the steps in the scaffolding. Really, we've done that, the base layer in some sense, and we're building the layers on top to allow us to do that. I think over the next few years, we'll start to see this in more specific domains to start with, where the experts or the domain experts can leverage machine learning. We'll start to see more applications that leverage machine learning behind the covers. So if you are used to things, so let's say Excel is a tool that lots of people do. Now they are used to certain kinds of functions, but a number of more things can be integrated into that to really help you, where you don't think that that's machine learning, but that really simplifies what you're trying to do. Another example that comes to mind is there's this company that I saw recently. Traditionally, if you think about something like photo editing, where you had to really mark pixel by pixel and sort of go through and define things that here's the part that I want to color differently and so on. Now, what they've done is they use machine learning to segment the image automatically. And instead of you saying, okay, these are the pixels they want, you just say, okay, I want to replace this person, or I want to change the hair color, or, because it's identifying all those pieces and making that logical. So from a domain perspective, you don't need to understand how the pixels work. If you're an artist, you can really work at the level you think at. And that's, I think, something that we need to see in different kinds of areas over time. I think we'll probably go more domain by domain, although the underlying technology is also slowly moving up the stack to make it easier.
Okay, I think we have a stream of questions as you might have expected. So let me go through the audience question one by one. We have about 8 minutes now. So the first question is, you covered TensorFlow as a tool. When is it the right time to switch to new tools or focus on basic algo?
So depends on what you're trying to do, right? If there's a trade-off of, if you have a tool, you're going to do everything that the tools allows you to do. We talked about the hammer. You basically can hammer anything. So even if you have a screw, you're basically be hammering it into the wall. Now, often that does work. Things like TensorFlow are very generic in that they, depending on the level that you're looking at, if you're looking at very high level, maybe it provides packages for certain things. As you go deeper down, it probably allows you to do more things and control more things in a different way. That said, maybe there are places where, if you're doing cutting edge research and you really want to play with some very, very specific things, like maybe you want a tool that's really focused on that kind of research. There are tools that either build on top of TensorFlow or PyTorch or something else focused on, say, natural language. And maybe that's the kind of tool that you want to use if that's the research that you're doing. Or sometimes you actually want to say, you know what, I don't even want the basics that you have. I really want to play with the math myself and really look at all those things. And then maybe even going back to the lowest level tools like NumPy, or, well, maybe, something like TensorFlow or PyTorch are still better because they can accelerate things with GPUs, but say MATLAB or something might be simpler. And so, yes, picking the right tool for the piece is definitely important. And TensorFlow, while it is very general and allows you to do a whole bunch of things, which is helpful in certain cases, if there's a very specific piece that you want to do, sometimes there's a better tool for doing just that.
Okay, thanks, Rajat. One related question, since we are already on TensorFlow, from Monica Rudra. Where are we on integrating Spark with TensorFlow?
There are, depending on what you're trying to do, there are a number of integrations already existing. So you can, the easiest is if you want to run inference or make predictions on data that lives, that you are sort of processing with Spark, you can do that pretty easily. There's a bunch of integrations available for that. If you want to train a model, that training piece is sort of independent. The Spark has a very different model than what TensorFlow uses. So you probably can't just use Spark for that. You would probably want to use TensorFlow's training or distributed training for that. In terms of data access, you can access, there's integration for accessing Spark data frames and stuff, and a number of things that there's been a lot of progress on. So I would say just look for that. And I think most of the things that you want to do are probably available today.
Okay. Now here is something which you showed and which also impacts us possibly on a day-to-day basis. How do we address deepfake? Can we use so in general, the question is, how do we address deepfake?
Yep. And I mean, that's exactly the example that I showed. And, there are lots of negative uses of that being done today. It's a hard one. It's one of those things where the technology allows you to use it in both good ways and bad ways. Can we use the same or similar technology to detect some of those? Yes, there's a lot of work happening in there. There's research happening to separate out, deep fakes from real videos as well. And I think we'll make progress there. But that said, it's sort of a cat and mouse game. If you think about things like, whether it's email spam or security, et cetera. Yes, you make improvements in catching all the existing things, but the folks who really care about getting around it would also come up with new areas as well. So I don't think there's a perfect answer there. We'll make improvements in both directions, and you'll see problems as well. I think a bigger question for us as society is, this is just a really, really powerful tool, and how best do we figure out, how do we manage that as a society? How do we put the right rules in place, potentially the right laws which do restrict the right kind of things? But also, how do we use them? What are the ethics that we live by in supporting these or not?
Okay, I think we have time for two more questions. Here is one interesting one, and which also reflects the pain that we as people involved in this field experience. Huge amount of, and this is from Rakesh, a huge amount of data is required for training most of the ML algorithms. Data collection for training itself is a tedious job. Can you give any ideas to make this process simpler?
Well, so sadly, there's no magic there, and people often don't realize that there's a lot of time and effort spent in creating that data. I talked about those data sets, ImageNet or speech or language. The researchers spend a lot of time really curating and cleaning up that data, and the same thing works for most models that you see. Now, it's not lost for every single thing, though, depending on what you're trying to do. If you're trying to really use do improvements or build a speech model or a vision model or a language model, where you can leverage something that's trained on existing data, then in which you can often today, then those models are available today publicly already, and you can start there and just fine tune on a very small data set and still get lots of benefits. Of course, if you're doing this on say a database that you have and you want to train that on those, then you still have to clean up your data and manage that and stuff. Although, of course, with that particular case, what you're trying to do, you already have the data. It's not like you need to label it manually and stuff. Now, the other good side of the labeling part is that itself is getting better. There are a lot more tools and companies that are helping make that better. So hopefully you'll see that getting better.
Okay, here's another one from Srinath. Despite the usage of many MLDL models by the top companies, the progress seems to be taking a long time to reach the typical enterprise, though. Could you let us know how to bridge the gap between research and real products?
Absolutely, and that is something that I think is a big deal. And in fact, this whole talk that things that I talk about, like TensorFlow Extended, is really the goal is to simplify that. And this is something we saw at Google as well early on, where early on the research teams would do that, and then some folks here and there who really understood the technology could leverage it. But as we started to build the pieces around the core model building itself, that started to help that. And I think we're making a lot of progress in that. The other one that came up earlier was, can we automate more of this? And we're starting to see tools both in open source and by companies that are helping those along. Some of the AutoML algorithms are available in open source with TensorFlow and other tools as well that you can start with, and also for some of the other pieces. And then there are products from companies that try to solve that and automate that for you as well. So it's a combination of those. But yes, it's definitely slower than I would like, and I think there's a lot more that can be done in terms of those pieces. The other thing I expect to happen is more of the areas or the applications themselves or the application makers will start to integrate ML, and that's how you'll see more of the stuff happening in enterprise.
Okay. Now, Rajat, here's one question which people keep asking us in classrooms and so on. Do we really need to understand maths and statistics to do machine learning and AI?
So I think it's gotten to a point where the short answer is no, you don't need to understand everything to get started. I think you can apply AI in specific areas without necessarily understanding all the pieces, and that's okay. I don't think I expect every engineer to learn all the details on day one. That said, if you want to make a lot more improvements, if you really want to push the state of the art, if you want to do research, then absolutely you need to understand a lot more. I think the good thing with the tools, the existing models availability, etc., has made so much progress that you really don't need to start by learning all the math. So that's definitely a good thing. I don't know if you would agree from a teacher perspective, where you do want people to learn that and there's value, but at least people, it's making it easier for people.
Yeah, I mean, like you mentioned, finally it depends on the goals, right? I mean, so long as the tools are getting more sophisticated and they are guaranteed to give you maybe not the wrong solutions, they are fine. I mean, you can, otherwise progress will never be made, right? Okay, here's a question from Pranay, and this one is very generic in the sense that will the ML automation on long-term basis be hazardous for human beings, looking at the machines becoming more and more intelligent on their own? So are we really pushing the envelope too much?
We think about this, this question comes up a lot, but it turns out, I mean, personally, I think eventually we will get there and we will have to grapple with those questions. And so something that we shouldn't completely ignore. But that said, if I look at the progress we've made and where we are still, there's still a long way to go in a number of directions, both from the computation perspective, from the algorithms perspective, and all the pieces that we need to put together for machines to be really that smart where they can do things that we may not like, etc. Today, yes, they can do things that we may not like, but they're usually going to be driven by some other human that's making that decision. For example, autonomous drones that kill somebody, right? So it's still being driven by or directed by somebody. The things I worry more about is just simple things like automation. Just like automation in the past, going from simple machines to computers, or even to an industrial age where instead of cows and farmers changing to tractors and larger scale things, caused a lot of changes. AI and machine learning here has the potential, and in fact it's already doing, allowing us to automate a lot more things that humans do today. Now the good side of it is these are often very routine tasks that these humans are not necessarily happy doing all the time. But that said, if that's their livelihood and they have to rethink how they make money, that is going to be a big change for them. And how do we get through that? That is a real challenge ahead of us very, very soon. And that's something that we should be thinking and spending more time worrying about.
Thank you, Rajat. There are many more questions, and more pertinently questions like how do I get hired by Google? I will let you write a book on that. I won't ask you that question. So since we also have come to the end of this time slot, I would like to thank you for your time and for giving us a glimpse into the various technologies and also answering the questions about the present and the future. Thank you once again, and it was a pleasure listening to you.
Thank you. It was a pleasure being here as well.